Hello, my name is John Garrett, and this is my Physics 2 Lab 3. So, quick introduction. The purpose of this lab was to determine the voltage and current in a variety of electrical circuits and then use multimeters to measure any kind of current or potential difference in those circuits. And some of the results that we got from this experiment were that the current remained the same throughout the entire circuit. The sum of potential differences were all about zero, just some tiny errors. And the charge and discharge times for the capacitor were also about the same. And just some fundamental physics principles that we used for this lab. The node rule, which just says the total current entering a node has to equal the total current leaving the node. The loop rule, which says that the sum of all potential differences around any closed loop is zero. Ohm's law, which is V equals IR, voltage is equal to current times resistance, and the capacitance, which is Q equals CV. So first for our series circuit, which you can see us using down here, the system of this was these batteries, wires, ammeters, and resistors. They were all connected in that circuit, and the surroundings was just everything else that wasn't the circuit. So the predicted current, which is using the equation I equals V over R, that's 3 volts because both of these batteries were 1.5 volts. Then you add up the two resistances and you divide the volts by the resistance, you get 2.04 milliamps. And then our actual current, which is what we measured, so for the 47 ohm resistor, it was 0.927. The 100 was 1.95. You add those together, you get 2.877, which is, you can round that up to 3 volts, which is about the same. So our prediction was just about on point. The currents that we got for the I1 was 14 amps, I2 was 14.9, and when you reverse that current, it's also 14 because it should be running the exact same way forwards as it is backwards. And here is our graph down here for what happens when you what's happening to the current right here. So as you can see, jumps up with these two batteries right here up until we hit the 47 ohm resistor. It'll drop about a volt, and it'll keep constant for a short little bit before it hits the 100 ohm resistor, and then that current is going to drop back down to zero, and it's going to remain at zero going back around the loop because the loop rule says that the sum of all potential differences must be zero. So that's just basically what this graph is showing right here. And just a little continuation of it, we also had to calculate out the individual potential energies. And so as you can see, we just use the formula for resistance for that. You can see here. So this is the resistor. Our resistor 1 was 1.94, and our resistor 2 was 1.90, and the wire and ammeter negligible, so those are 0. So for the RC circuit, what we saw was that the light bulb rapidly gets brighter as the capacitor charges because there's a lot of current hitting that light bulb at one time. But as the capacitor is charging up, that light is going to get dimmer and dimmer and dimmer because that capacitor is now holding charge that is not making it to the light bulb. And then as the capacitor is discharging, it's going to get brighter for a little bit because there's a little extra current flowing through into that bulb, but then eventually will just dim all the way back down. And so as you can see here, we had a 10 and 20 ohm light bulbs, which were our resistors. And so as you can see here, the charge time for the 10 was 18 seconds. Its discharge was about the same, which is right. It's about 17.5 seconds. The charge time for the 20 was 9.8 seconds, and the discharge was 10 seconds. So they're supposed to be about the same as each other. So nothing abnormal there. And then for our potential sources of error, it's possible that as we were attempting to connect the ammeter, voltmeter, or multimeter at various points, that we may have touched the circuit or we may not have connected them correctly, which could lead to some incorrect values for what exactly the charge was at that point in time. And we also had some faulty equipment during the experiment as well. So we did have to switch equipment multiple times during the experiment because it was malfunctioning from extensive prior use in other labs. So that also could have affected some of our values because some of these values came from the old equipment, some of them came from the new equipment. And for the discussion, theoretically, charging a capacitor without a resistor would cause the capacitor to charge instantly because electrons move essentially in the blink of an eye. And so it would look like this capacitor is charging nigh instantly. But in real life, this isn't possible because the capacitors have constraints that are not shown in theoretical models, and then the ammeter that we're using to measure the charge will also provide a very slight resistance, not a big one, but a very slight resistance, and so that'll also keep the capacitor from charging instantaneously. All right, thank you, and thank you for watching.